All right, I'm back. It's time to talk about reasoning. It's like shockingly quiet in my room. My clock isn't quacking and my air conditioning's not running. I feel like I should hurry so I can get it out before the noise starts again. Reasoning. Okay, let's do an example here. So you're looking at 4 cards. Imagine that, they're regular cards that you could flip over. Currently, you're seeing one side of each card. You could flip it over, and if you're currently seeing a triangle, on the back is going to be a circle. If you're currently seeing a circle, on the back is going to be a triangle. What is unknown is what the color of the object on the other side is. So if you flip over the black triangle, you're definitely going to find a circle on the back, but you're not sure if it's going to be a black or a white circle. If you flip over the circle, it's going to be a triangle. You just don't know if it's black or white, and so on. So our hypothesis is that if there's a black triangle on one side, there's a white circle on the other side. Okay. So your challenge is, which card or cards must, I want to emphasize must, you flip in order to test the hypothesis. So we're not going to flip all 4 and just see what's on the other side. We're going to try and flip as few cards as we possibly can in order to answer the question, to test the hypothesis that if there's a black triangle on one side, there's a white circle on the other. So which card or cards must you flip? I would like to argue that honestly you only need to flip 2. So try and figure out which 2 you would flip over. And then I will go ahead and tell you what you should be saying. All right. So if you were to flip over the black triangle, which is the most popular one to flip, almost every student wants to flip the black triangle. That's not a bad idea, because if you flip it over and you find a white circle, then you have evidence that supports the hypothesis. If you flip it over and you find a black circle, then you have evidence that refutes the hypothesis. So the black triangle is very attractive, and most people want to flip it. Okay. The next most popular one to flip is the white circle, because they want to flip it over and find out if there's a black triangle on the back. This would support the hypothesis, right? If you flip over that white circle and you find a black triangle on the other side, then you'll say, well, I've got a black triangle on one side and a white circle on the other, so I've got support for the hypothesis. The problem with the white circle is that it doesn't have any ability to tell you whether your hypothesis is wrong. It has no ability to refute the hypothesis. If you flip over the white circle and find a white triangle, that doesn't really do anything about a hypothesis that predicts that if there's a black triangle on one side, there's a white circle on the other. Right? It doesn't say anything about what has to be on the other side of a white circle. It says what needs to be on the back of a black triangle. So the next most popular, every time, every class wants to flip the black triangle, and then they want to flip the white circle. So if that was your instinct, you're right there with most people. If you said, I want to flip the white triangle, you wasted a flip, because that's actually just there for symmetry. Because if you have a white triangle associated with a white circle, I already explained that that's not going to refute the hypothesis, because the hypothesis only goes the one direction. Black triangle must have a white circle on the other. So yeah, that white triangle doesn't do anything. My personal argument would be that you should start by flipping the black circle. Because if you flip the black circle and you find a black triangle on the other side, your hypothesis has been refuted, and there's no point in looking at anything else, right? Not even the black triangle, because we already know the hypothesis is wrong, because it doesn't cover every black triangle. Because if I flip over this black circle and find a black triangle, we have a black triangle with something other than a white circle on the other side. There's no point in testing any farther. The hypothesis is wrong. So if we find a black triangle, we have evidence that the hypothesis is wrong. If we flip it over and we find a white triangle, well, it doesn't do anything for the hypothesis. So then if that happens, so if it were me, I would start by flipping the black circle. If I found a white triangle on the back of the black circle, then I would go to the black triangle, but only to see if it has a black circle on the back. If it has a white circle, that doesn't tell me I'm right. It just tells me I'm not wrong yet. Right? Like, I need to find some more black triangles and more white circles to flip over to keep testing. But for this population, I'm not wrong yet. The power of the confirmation bias to look for evidence that we're right is what drives us to want to flip the black triangle and flip the white circle. We want to find evidence that we're right. And the white circle is really powerful because we think we're being clever. We're like, what? Here we have a white circle. Let's see if there's a black triangle on the back. Oh, yay, there is. Yay, I was right. And we even have that feeling. Yay, I was right. But we were right in the face of a situation where we couldn't have possibly been wrong. So how rewarding really is that to be right? So in reasoning, we want to make sure that we are following proper protections to make sure that we're actually thinking in a way that would show us if we're wrong. So there are different types of reasoning that we can use. Deductive reasoning is when we reach a conclusion based upon true assumptions. So we oftentimes will call this propositional reasoning. In this kind of propositional reasoning, if the logic flows one way, it must flow the other. So if you mistakenly thought, well, if there's a black triangle on one side, there is a white circle on the other, means if there's a white circle on one side, there must be a black triangle on the other. If you made that logic, you were using deductive reasoning. You were using propositional reasoning. It's an erroneous deduction to conclude that a hypothesis is propositional. Hypotheses have to be super specific. And so if it was supposed to be and vice versa, it would need to say and vice versa. But our natural tendency in our deductive reasoning process is usually to do that kind of propositional reasoning and to just sort of mentally think and vice versa. Under deductive reasoning, there's also something that we call a categorical syllogism. Categorical syllogisms refer to some, all, or none of the possible events. Let me give you an example. It'll make more sense. So, for example, if we said all A's are B's, all B's are C's, we would have to logically conclude that all A's are C's, right? Because if all A's are B's and all B's are C's, it logically flows that all A's have to be C's. So let's apply that with an example. All Seattleites drink coffee. All coffee drinkers are irritable. Therefore, all Seattleites are irritable. Okay, that feels wrong, doesn't it? Logically, it's correct. In practice, it can't be correct, right? So one of the first things we all want to do is say, I'd rather do some. Can I do some instead? All and none, those are fighting words, aren't they? You never do that. You're always doing that, right? Like those are fighting words. Some is better, it's softer, it's nicer. It takes into account that there are variations and people might not all do the same thing. So let's try some. So some A's are B's. Okay. Some Seattleites drink coffee. Okay. Some B's are C's. Some coffee drinkers are irritable. Yeah, that's true. Some A's are C's. Therefore, some Seattleites are irritable. Okay, that feels better, doesn't it? That feels good. It feels like now I haven't tried to be so black and white and so, hard-edged about it. I'm taking into account that not everybody drinks coffee. I'm taking into account that not all coffee drinkers are irritable. And I'm recognizing that not all Seattleites are irritable. Okay, this feels better. Let's put something else in there and see if it still sounds better. Okay, some A's are B's. Some dogs are Seattleites. That's true. Some dogs live in Seattle, right? Some B's are C's. Some Seattleites are cats. That's true. There are cats that live in Seattle. Okay. Some A's are C's. Therefore, some dogs are cats. Hold on. That can't be true. Unless you guys are of the age where you ever saw that Nick Jr. show called Cat Dog. But that's not real. That's a cartoon. So some dogs are Seattleites, some Seattleites are cats. That's sounding really good, but then the logical conclusion that flows from it has got to be wrong. So it turns out that while some sounds better, all or none are the logically safer bets because you are more likely to be logically correct. Okay, those of you who have had philosophy are like, yep, I know what you're talking about. Those of us who have never had philosophy are going, wait a second, I don't like what you're saying. It doesn't make sense. When we are making decisions or we are trying to reason about things that are happening in our world, our tendency to try and say some and not be overextending our judgments or whatever causes us to draw incorrect conclusions oftentimes because we leave things out by accident rather than on purpose. Like if you're going to follow the logical syllogism of the all, let me get to the alls again real quick. If you follow the logical syllogism where it's either all or it's none, you're going to have to be really careful about defining exactly your sample or exactly who you're talking about. I can't make broad strokes like Seattleites. I might have to say, people who visit Starbucks drink coffee, right? I might have to start getting more specific in order to make my data fit the logical conclusion of this deductive reasoning. And that makes us much more careful, right? It makes us generate hypotheses that are more specific to our samples and things like that. And so while it might not be our natural way of thinking, when we're doing science, we probably should be thinking like this and being really super careful to be logical rather than like covering our bases and as a result ending up with less precise definitions. So now the transition that I wanted to make is a little rough here because I wanted to talk next about how computers go through the process of making decisions and reasoning and things like that. And so I found this nice TED Talk where he's talking about whether computers and other kinds of computing machines can really think like humans. So go ahead and take a little visit with this TED Talk and I'll see you on the other side.